This is part of a series of lectures that I'm creating to help my students better understand what binary and what hexadecimal is. But before we start into converting between bases like most people do, I'd like to take a minute and try to open your mind a little bit and regress a little bit to some things you learned in the past and really understand what a number's base actually means. So let's start with something familiar, of course, and start with base 10. Base 10 is a numbering system that we use every day, but we never really start and think, what does the 10 in base 10 actually mean? Well, we never really think about the fact that it is base 10. What does it mean that it is base 10? Why is it base 10? And that is because we have 10 symbols to represent all quantities. We're so used to seeing those symbols every day that we've stopped and we've just automatically mapped each one of those symbols to a quantity. For example, the number 0, that little circle we use to represent a quantity of none. And in this case, this symbol is going to represent for us the fact that we have no kittens. So we're using that 0 to represent the fact we have a lack of kittens. If one kitten were to come along, then we would move one symbol to the right to represent the fact that we now have one kitten. As more kittens come along, we just keep moving one symbol over to the right to represent that quantity of kittens. There's 4 kittens, and 5, and 6, and 7, and 8, and 9. Now, the problem comes whenever we get to 9 kittens. We've run out of symbols, essentially, to represent our quantities. So what do? Well, what comes after 9? Of course, 10 does. And what we're doing is we're adding another symbol to the left of the number. What that symbol is actually telling us is how many times, how many iterations we have gone through our list of symbols, 1 over to the right. This 1 in 10 is telling us that we have gone through all of our 10 symbols one time, giving us a quantity of 10. If that is hard to visualize, I like to picture a speedometer or a simple counter. Here I've added a simple counter that's counting up to 100. And if you just stop and look at it or visualize the counter, when do the numbers change? The number on the right changes very frequently because it represents a single. But the number to the left of the number doesn't change until we have used up all the symbols 1 to the right, representing all possible quantities in base 10. A higher number just means more symbols, or another symbol to the left. The symbol to the left that's always there that we never see is 0. We can add as many zeros to the left as we want, and it doesn't change the value because it's a symbol of none. It's a symbol of 0. We represent this a little bit more mathematically by writing numbers out in long format. Probably something you learned a long time ago and let slip out of your mind because you never really use it. Consider the number 42. What does the number 42 actually mean? Well, the number on the right, the 2, means 2 singles, and the number on the left means 4 tens. We've gone through all the numbers on the right 4 times, giving us a quantity of 40, and we're currently sitting at 2 on our singles, and that's a 2, or 40 plus 2. Written out a little bit more scientifically, we can write that out as 2 times 10 to the 0, or 4 times 10 to the 1. A lot of people make a mistake right here by forgetting that any number raised to the 0th power is 1. So always remember that. So 42 can also be written out as 4 times 10 to the 1 plus 2 times 10 to the 0. Doesn't matter how many positions you have, you just have to remember that each number to the left represents a power of 10. 24,789 also represents 20,000 plus 4,000 plus 700 plus 80 plus 9. Each number telling you how many iterations the one to the right has actually been through. We could also write this out as 2 times 10 to the 4 plus 4 times 10 to the 3 plus 7 times 10 to the 2 plus 8 times 10 to the 1 plus 9 times 10 to the 0. Each exponent going up 1 as we move to the left. This is important to note because this is how we're going to translate binary numbers into decimal numbers. So now let's see an example of another base, base 2. In base 2, instead of having 10 symbols, we only have 2 symbols, hence the bi in binary. With these 2 symbols, we can represent every quantity. We just have to do the same thing that we do with decimal and add and continue to add numbers on the left to tell us how many times we have gone through the iterations on the right. So let's start again with no kittens. We have 0 kittens. Well, we haven't run out of symbols yet, so there's nothing suspicious here. There's nothing crazy here. We just use the 0 to represent our lack of kittens. When 1 kitten comes along, we have a single kitten, and we haven't run out of symbols yet. We still have that 1 that we can use to map to that quantity of kittens. The problem, if we have 2 kittens, let's have another kitten come along, then we have a problem because we only have a 0 and a 1 in binary. So what do? We do the same thing that we do with decimal, and we add another symbol on the left. And just like whenever we go from 9 to 10, or 9 add 1 and you get 10, when you add 1 to 1 in binary, you get 1, 0. The 0 on the right saying we have no singles. The 1 on the left, I should say, represents the fact that we have gone through the number of the symbols on the right 1 time, giving us a quantity of 2. Got 0, 1, and now 2. If we add a third kitten, we just change the 1 on the right, or the 0 on the right, to a 1, giving us 1, 1 to represent 3 kittens, because that's all the symbols that we have available to us. It's no different than base 10. It's just the fact that we're not used to doing a mental mapping from 1, 1 to 3, or to a quantity of 3, than we are with using base 10 and seeing the number 3. If we add a fourth kitten, we've run out of symbols again, so we just add 1 to the left. If we were to create a counter in binary instead of base 10, then you might be able to see the difference as well, or to better visualize it, I should say. Here we go. The number all the way on the right only has 2 possibilities. It can only swing between 0 and 1. The number 1 over will tell you how many times this number has changed. This one will tell you how many times this number has changed, so on and so forth. It works in the same way as decimal. It's just you have fewer symbols to represent your quantities. Oops, I paused it for a second and the counter kept going there. But as you see, the numbers just keep progressing until it runs out of symbols, and then it has to move a 1 over here, 0 everything out, and then start all over. We can also write this out mathematically by using the powers of 2 instead of the powers of 10. So 2 and 3, those are base 10 numbers. We can actually convert the number into its decimal equivalent. For example, 100110 could also be represented and converted by writing it out in long format using the powers of 2 and the exponents that correspond to the positions of the zeros and ones. For example, 0 times 2 to the 0, 1 times 2 to the 1, 1 times 2 to the 2, 0 times 2 to the 3, 0 times 2 to the 4, and 1 times 2 to the 5. I'm going to stop here, but if you'd like to continue on, watch the video on binary to decimal translations that follows this video, where I'm going to continue this procedure and show you a quick way to translate binary into decimal.